So we're now going to talk about the last topic related to C++ class and function templates. And this example is a really fun example because it's going to get us a chance to talk about some more advanced topics. I'm not going to require you to be fully versed in all these advanced topics. I really want to focus in on one specific aspect of this as it pertains to templates, but the example is just too much fun not to show you. So don't worry, the things we're about to talk about with respect to multi-threading and synchronization won't actually be part of any quiz, but I'm going to use this to motivate a particular feature in C++ templates that's very cool. So let me run the program for you and you can see what it does. And what the program does is not build. Let's see if I can get it to build without starting from scratch. There we go. So I'm going to go ahead and run the program, and you can see what the program does is it says ping 1, pong 1, ping 2, pong 2, and so on. So it basically has a pair of threads, and one thread is the ping thread, and the other thread is the pong thread, and they alternate saying ping and pong, and then letting the other thread go. So this is a good example of using something called a semaphore as a coordination mechanism to allow two threads to interact in a very stylized and disciplined way. So that's what the program is doing. So let's go ahead and take a quick look at the program, and then I'll zero in on the part I really want to focus on, which is the use of Variadic templates. So the program, as you can see, is going to have a number of threads. In this case, we have 2 threads. What is a thread, you might ask? A thread is basically a unit of computation that runs in the context of something called a process. So a thread is how you do the computation. It's a stream of instructions, typically these days mapped to a core, like a core in a multi-core processor. And you can have more than one thread running in the context of a process. And a process is essentially a unit of protection and resource allocation to allow one or more threads to do their thing. So that's what a thread is. You don't have to know too much about threads. I promise not to ask you questions about threads on the quizzes, but they're good things to learn about because many later courses at Vanderbilt will leverage threads, including some of the ones I teach. We then have another const, which is the number of iterations. As you can see, if you look at the output, I run this for 4 iterations, but of course I could make it more than 4 just by changing that constant. Here's the main program. I define myself an array of num threads where num is 2. So I have 2 threads, the ping thread and the pong thread. And then I print a little diagnostic message, and I'm about ready to start running my threads. But before I do that, I'm going to create 2 semaphores. Now, a semaphore is a so-called synchronization mechanism. And the term semaphore comes from way back in the day when people used to travel by train. And when you traveled by train, you'd often get to a point, especially near a big city, where train tracks would converge. So you might have multiple train tracks coming in and they would share a single track. And they had these things called semaphores, which were basically kind of like stoplights or flags or signal towers that would indicate whether or not the track was shared and someone was on it, it was in use, or whether the track was available. And so the 2 concepts in a semaphore are available for use or in use. So the way we phrase it here is kind of locked or unlocked. And the particular way we're using these semaphores are things known as binary semaphores, which, as the name applies, has 2 states. They're either unlocked, which is the value of 1, or they're locked, which is the value of 0. So that's at a high level, that's what a semaphore is. It's basically it's a count that has certain properties based on the current value. We'll talk more about that in a second. Down here, we go ahead and we create ourselves a thread. So thread sub 0 is going to be allocated a new thread, and then thread sub 1 will be allocated another thread. And this is actually the whole point of this discussion, is to show you how the thread method works in C++ threads. So take a look. If you take a look, when we create a thread, we pass it the name of a function we want to have executed in a separate thread of control. So when you start running your program, when you have a main program, that's typically going to run on the main thread. So there's always one thread that exists. So we're going to have the main thread then create two other threads. One thread will be the ping thread, the other thread will be the pong thread. And so when we do this, we have to give the thread that's being created a function to run. And this function is called play ping pong. And if you go and look at play ping pong, here's the play ping pong function. And you can see that the play ping pong function takes 4 parameters. It takes the number of iterations to run. It takes a string to print, which will either be ping or pong. And then it takes a pair of semaphores, one of which is known as my semaphore, and the other which is known as other semaphore. And we'll see how those things get used in just a second. The semaphores are used to coordinate the two threads so that they take turns alternating printing ping and pong. Once the play ping pong method has been called with its parameters, it goes into a loop, and it loops for I equal 1, I less than or equal to max iterations, and it increments the loop count every time through the loop. And what we do is we start out by acquiring my semaphore, and I'll talk about what that means in a second. Once we've got the semaphore, then we go ahead and we print out the loop and the loop count, 1, 2, 3, etc., and what our string to print is, either ping or pong. And then when we're done, we release the other semaphore. Now, to make sense out of what a semaphore does, it's got 2 operations, at least 2 operations, but 2 key operations. Acquire, which says wait until the count of the semaphore is greater than 0, and then atomically decrement the count and proceed. That's what acquire does. And release says atomically increment the count of the semaphore. And if somebody is waiting for the semaphore to be non-zero, then when you release it, they can go ahead and run. So we're basically using these semaphores to have the threads signal each other when they want to run, and after they're done, then the thread signals the other thread it's its turn to run. Okay, and we'll come back and talk more about that. The real thing I want to point out here, though, is that we have 4 parameters to the play ping pong method. And you can see here that indeed we have 4 parameters passed after we pass in the play ping pong method as the first parameter to the thread class. And as you can see, we pass in max iterations, we pass in the string, either ping or pong, and then we go ahead and we pass in the ping semaphore and the pong semaphore in the case of the ping thread, or the pong semaphore and the ping semaphore in the case of the pong thread. So you can see that we're swapping them in the 2 different methods. So why I want to point all this out is that if you take a look at thread, if you go look at the implementation of thread, here is the thread class that we're using to make a new thread. And this is part of the C++ standard library. It's actually not strictly part of STL, but it's using the Variadic template features we've talked about before. And without getting too wrapped up around the axle of what is a thread, I want to direct your attention down here to the constructor of thread that we're using. And here it is. This thread, as you can see, takes 2 parameters. The first parameter is going to be an R value reference to something known as a callable. And I think you'll probably agree with me that passing in the name of a function is a good way to get something that's callable. And then the second parameter, which is actually, as you can see, a variadic set of parameters, is this funky args variadic template. Now, if you go and watch the videos that I posted earlier that talk about variadic templates in the context of the adder example, for instance, you'll see that what you're doing here is you're really providing a placeholder for an arbitrary but fixed but arbitrary number of parameters to be passed in after the callable. So as you can see here, we pass in play ping pong, and then we pass in 4 parameters. And it just happens that 4 parameters is exactly what play ping pong expects. But notice how this is a variadic template, and it's used to allow strongly typed passing of fixed but arbitrary numbers of parameters. And then underneath the hood here, there's some super duper magic that's going on inside this method that's going ahead and invoking some internal method called invoker, and it's passing in the callable followed by the args, and then it goes ahead and starts the thread, and it goes ahead and passes all that information in here. So essentially what this is doing is this is arranging to call whatever the callable method is, which in our case is play ping pong, followed by all of the arguments that were passed there. And they're all put together into basically a bundle, and then they're forwarded to the callable. And I won't get into the low-level details of how all this works, but this is some C++ template magic that moves these values very efficiently and then arranges so that the method play ping pong will be called with the appropriate number of parameters that were passed to it. And all this can be strongly type checked. So if we were to pass the wrong number of parameters there, then we should get a compile error, because it would say, hey, you can't do this. You don't have the appropriate match between the number of methods, the number of parameters that you're passing to thread, and the number that are expected by play ping pong. So the key point I wanted to show you here was this concept of how you can have variadic templates applied in practice for something very useful, like creating threads whose functions take a variable number of arguments. Fixed, but variable. Just because we're here, let me go ahead also and show you how semaphore is implemented. So the semaphore class actually, for some strange reason, does not exist in the C++ standard template library or the standard library. So we're going to implement a semaphore using a pair of other synchronizers that are, in fact, part of the C++ standard library. And those other classes are mutex and condition variable. And a mutex is a mutual exclusion object that only allows one thing to go at a time. And a condition variable is a coordination object that allows threads to put themselves to sleep until something changes to their liking. So let's take a look at how you might implement a semaphore using a mutex and a condition variable. This, again, is a bit beyond the scope of the class, but it's fun. And so I'll give you a little preview of things you'll cover in other courses as you get further along. So here's the semaphore. You will give it its initial count, which in our case was either 0 or 1, where 0 meant locked and 1 meant available. And then we have a pair of methods, acquire and release. We'll talk about them, look at their implementation in a minute. And then down here, we have the actual implementation of the semaphore itself. And you can see we have 2 data members, one mutex m and one condition variable con, and those are used for synchronization and coordination. And then we also have n, which is the count, the current count of the semaphore. So let's go ahead and take a look at the implementation of this. You can see that the constructor is very simple. It just sets the count to I, whatever you pass in, the initial value. That's what n becomes. Let's take a look at acquire. Acquire uses this really cool scoped locking idiom, which I think we've talked about briefly before, and now we'll look at it again. It basically uses the C++ trick of resource acquisition is initialization. So when we come into acquire, there's a lock variable defined, which is defined to be a so-called unique lock, and it's parameterized by a mutex. And what unique lock does is it goes ahead and locks the mutex m. And I think we've looked at unique lock before. Let me just go show you to refresh your memory what unique lock does. So you can see what unique lock does. Its constructor goes ahead and essentially will take ownership of the lock. It'll lock the lock. You can see it down here. It locks the lock. So that's what the constructor does. And then you can see that there's a destructor lurking here somewhere, which goes ahead and unlocks the lock. So that's why it's called scoped locking, or resource acquisition is initialization. So the long and the short of it is that only one thread at a time can actually be running the code inside of the acquire method. And if more than one thread comes in at the same time, then the subsequent ones will wait on the lock until the lock is released. Now, as it turns out, if the value of the semaphore is equal to 0, if the value of the count, n, is equal to 0, we want the semantics to be to go to sleep and wait until the count is greater than 0. So that's what it means to acquire a semaphore. You can only acquire the semaphore if its count is greater than 0. Otherwise, you have to go to sleep. And to do that, we use the the wait method on the condition variable. And when you call condition wait, you pass in the lock, which is this guy. And then we go ahead and we pass basically a predicate lambda function that says, don't come back until n is greater than 0. That's basically the condition that we're waiting on. And we have to use this little thing called a capture clause here because it's a lambda function. And we're saying you can take the state of this object in order to do this. So that's acquire. That's the way you implement acquire. Here is release. Release likewise comes in, gets exclusive access to the state of the semaphore. Once it's got exclusive access, it increments the count by 1, and then it goes ahead and notifies anybody who might be waiting that they have a chance to wake up and try to get that semaphore if the count is still greater than 0. So anyway, this is just a little precursor for some things that you'll cover later if you take the operating systems course or if you take any of my courses on concurrent and parallel programming. And then we'll talk a lot more about this stuff. But the real reason I wanted to talk about this was not so much to show you concurrency and synchronization, but to show you how Variadic templates can be used for a very pragmatic purpose to be able to make it possible to pass in functions to the thread method, the thread factory method, that take a fixed but arbitrary number of parameters. Okay, so that's the end of this first discussion, and that's really the end also of our discussion about templates qua templates. So from now on, we're going to be using these concepts we've talked about in the context of other STL containers, algorithms, and functors.